Lecture 4 of Real Analysis on the Argument Channel, all about limits. So recall from the last lecture the definition of a limit. Limit as n approaches infinity of a sub n equals L, or you can also write it a n goes to L, the right arrow, if for all epsilon greater than 0, there exists n in the natural numbers such that n greater than or equal to n implies an minus L, the absolute value of that, is less than epsilon. So in this definition, n is only dependent on the value of epsilon. This So example, a sub n is equal to n over n plus 1. So if you've done calculus before, it's clear that it goes to 1, but let's use the definition here to show it. So let epsilon greater than 0 be given, then choose n equals blank. So we don't know what n needs to be yet. We're going to progress through this proof to determine what it needs to be. Now, suppose n greater than or equal to n, so this absolute value of an minus the limit we claim is 1 is equal to, if we sub it in, n over n plus 1 minus, and you can write 1 as n plus 1 over n plus 1 for reasons we'll see soon. And if you subtract inside there, you get negative 1 over n plus 1, and taking the absolute value now, that's 1 over n plus 1, and that's less than 1 over n. So that is also thus less than or equal to 1 over n, because n, small n, is greater than or equal to big N. And now we want this to look like it's less than or equal to epsilon. So we can choose n is equal to 1 over epsilon and just fill that out over here. And in our definition, n needed to be a natural number, and possibly this 1 over epsilon might not be a natural number. So we can fix that by just taking the ceiling. Right, so now we can conclude an approaches 1, or converges to 1, or the limit of the an's is 1. I guess that's how you'd want to phrase that. So some remarks. If for all epsilon greater than 0, there exists n, which isn't natural, it's now real for greater than 0, such that an minus L less than epsilon for n greater than or equal to n, then an approaches L. So this is just saying that we don't need our n to be a natural number as long as it's real and greater than 0, i.e. positive. Then it goes to L. and we won't prove this, but you can just use it. Example, an is equal to square root of n squared plus 1 over n factorial. From some calculus, we can show that lim an approaches infinity is equal to lim an, if you sub in for an, 1 over n infinity, the bottom grows a lot faster than the numerator, so that will make it go to 0. Let's show that formally. So an approaches L. Let epsilon greater than 0 be given, and same as last time, we choose n later, but I just write it in here so the proof flows. Choose n equals blank, and then assume n is greater than or equal to n. So we have a sub n minus 0 is equal to, subbing in now, n squared plus 1 over n factorial. This will always be positive, so we just got rid of the absolute value. And that's less than or equal to n squared plus n factorial, or n squared plus n squared, I meant to say, which is equal to square root of 2n over n factorial is equal to square root of 2 over n minus 1 factorial, because we took away at n from the top and the bottom. And finally, that's less than square root of 2 over n minus 1. So square root of 2 over n minus 1 is less than epsilon if and only if square root of 2 is less than epsilon n minus epsilon if and only if square root of 2 plus epsilon is less than epsilon times n. And finally, that's if and only if n is greater than square root of 2 plus epsilon over epsilon. So we're going to choose n to be square root of 2 plus epsilon over epsilon. Okay, so now we can conclude a sub n minus 0 is less than square root of 2 over n minus 1 is less than epsilon. So an approaches 0 as we wanted. As another example, for all L in R, there exists a sequence of rationals Qn such that Q sub n approaches L. So whenever you have a real number, there's a sequence of rationals that are such that the limit of those rationals is that real number. So find Q of n. So answer, let L in R, let epsilon greater than 0, and from before, for every, or for each n in n, there is a Q sub n q. The rational is such that qn minus 1 is the absolute value of qn minus 1 is less than 1 over n. As 1 over n approaches 0, there is an n in the naturals such that 1 over n is less than 1 over epsilon when n is greater than or equal to n. And for n greater than or equal to n, q sub n minus l less than 1 over n less than or equal to 1 over n is less than epsilon as we needed. So let's look at some more definitions. What it means to converge if an, the sequence, does not converge. To any L real, we say an diverges. So if an converges, then it's just the definition from before. For all epsilon greater than 0, there exists n in the naturals such that an minus l less than epsilon for all n greater than or equal to n. And now the opposite of that, a sub n, the sequence diverges if, let's take a look. We want to negate the statement above, so no matter what I guess we missed one part, that there exists an L. Now, to negate that, we say for all n in R, and there exists an epsilon greater than 0 for all n in the naturals, an minus l, so you negate it, so it's greater than or equal to epsilon. So let's look at an example of a sequence that diverges. So -1 to the power n. So this will just go oscillate between 1 and -1 as n approaches infinity. So let's show that it diverges by contradiction. So assume an goes to L. Then let's choose epsilon equals 1. There exists n in n such that an minus l is less than 1 for all n greater than or equal to n. So first we note that an minus an plus 1, let's write that nicer, is equal to 2. So that's just the general way to solve these types of problems. So you look at the structure of the sequence and find some trick in it. Continuing on, so assume n greater than or equal to n. We have that my writing's really messy. A sub n minus L is less than 1 because we're assuming that this limit exists. And a n plus 1 minus L is less than 1 because n plus 1 is greater than n, so that must hold as well. So if we write 2 is equal to an minus an plus 1, and we do a trick inside that absolute value, minus L plus L. So we're really doing nothing. We just subtract and add L. That is less than or equal to an minus L plus L minus an plus 1. That's through the triangle inequality. And that's equal to an minus L plus an plus 1 minus L. And we know that that must be less than 1 plus 1 is equal to 2. So we just showed here that 2 is less than 2 as a contradiction. So an diverges because it contradicts the assumption we made that it does converge. Okay, let's now look at how we can use limits to prove theorems. So you might have seen the squeeze theorem before. Here's a proof of it. Suppose a sub n is less than or equal to b sub n. So bn is between these two sequences. So there's a sequence an, there's a sequence bn, there's a sequence cn, and it satisfies these inequalities for all n greater than or equal to m. If an goes to L, and Cn also has that limit L, then Bn must go to L as well, because we're saying that it's squeezed by An and Cn. So doing that formally, from the definition, let epsilon greater than 0 be given. We're going to show that Bn has a limit L. There exists n1 and n2 in the naturals, so that n is greater than or equal to n1 implies an minus L is less than epsilon, n greater than n2. So the n1 and n2 is because the number at which the an minus L is less than epsilon might be different for the two sequences an and cn. So that's why we have this n2. And so for that, we have cn minus L is less than epsilon. So now if we just choose the maximum of them, n2, as well as m. So in case the Bn isn't squeezed until m. So now we can go through our usual proof, n greater than or equal to n. Therefore, L minus epsilon is less than an, and from the assumption that's less than or equal to Bn, and that's less than or equal to Cn, and from the from here, that's how we got this, and from to get this, that's from here, because n is greater than or equal to n, so n must be greater than or equal to n1, n must be greater than or equal to n2, since n is the largest of the two, or m. So continuing on to the proof, L minus epsilon less than or equal to B sub n less than or equal to L plus epsilon. Those are supposed to be strict. Less than, and then that means Bn is less than L minus, that's not that. Subtracting L from both sides, we get negative epsilon from all of the inequalities, and positive epsilon. And that's the same as saying Bn minus L is less than epsilon. Therefore, Bn goes to L. Done. And that's it for the lecture.